Hey there, folks. Good afternoon. The problem for today involves a long, thin rod of uniform density. It has a length of L and a mass of M. We're going to take this rod and stick a chunk of clay on one end, and that clay chunk will also have a mass of M. What we need to do is to take this weird-looking object and use it to solve four different parts. In part A, we're going to calculate its center of mass and then mark that spot on a picture. Then in part B, we'll balance this thing vertically on a frictionless tabletop and figure out what the angular acceleration would be if it gets tipped over at a small angle. Part C is basically a repeat of part B, except now it's the clay that stays in contact with the table. We're still going to tip this thing over and figure out the angular acceleration, but once we know the value, we need to compare that to what we found earlier in part B. And then finally, in part D, we're told about the difficulty of balancing a pool cue on one finger. Apparently, it's easier to do this with the thin end touching our finger compared to the thick end. We need to explain why, and we'll use the results from parts A through C to do that. Let's begin part A with the drawing. There are two things that we need to take care of before we can start calculating anything. The first is to draw the forces that are involved here. We have the weight of the rod and the weight of the clay, and that's it. The other thing that we should do is set up a coordinate system. Since the rod is thin, we only have to worry about setting up a horizontal axis, but we need to be careful how we do that. If we place the 0 point of that axis on top of a force, well, then it can lead to a bad answer. So I'm going to recommend that we stick x is equal to 0 over on the left side, like this. This location of x equals 0 will mean that the weight of the rod is at an x value of L divided by 2, and the weight of the clay is at an x value of L. Now we're ready to calculate the center of mass. And here's the equation that we'll use. I'll replace m1 and m2 with m, since the mass of the rod and the mass of the clay are the same. x1 will be the distance to the center of the rod, and x2 is the distance to the clay. I'm going to simplify this a little bit and then multiply the ml term in the numerator by a special form of 1. This will create a common denominator of 2 between those terms in the numerator, which will allow us to squish them together into a single fraction, like this. The 2 in the denominator of the numerator can be moved downstairs, and then ml plus 2ml will become 3ml upstairs. If we divide out m from our result, we get the following. So our answer is a center of mass that's located at 3/4 of the length of the rod, measured from the end without the clay. And if we go back to our picture to draw where that is, the spot will be located right around here. And that's it for part A. In part B, this object is now slightly tipped over from the vertical. And we know that if there's an angular acceleration involved, well, then there's got to be a torque. So let's get the force and lever arm of that torque identified. The force is the weight of this entire object. which acts from the combined center of mass that we just found back in part A. To get the lever arm for that force, let's draw the line of action for the weight, which is represented by this dotted purple line. And let's also label the point of rotation. I'll call it point Z. The perpendicular lever arm distance that we're looking for is found by drawing a line that connects point Z and the line of action, like this. That lever arm is going to be dependent on our angle, though. So we should try to find a way to represent it in terms of theta. And here's a really easy way to do that. Instead of playing around with the geometry, we can just slide this lever arm upwards. And doing so does not change its length. But now, it's clear that the sine of theta is involved here. And we can multiply that by the distance between point Z and our center of mass to get the value of the lever arm. And so, when we do that, here's what we end up with. There's no other forces that are contributing to the rotation, so we have everything that we need to get started on the sum of torques equation. On the left, our sum will contain only a single torque, which is the gravitational torque about point Z. And on the right, our moment of inertia variable will include both objects. Let's go ahead and keep things simple and just leave all the variables as positive. I'm going to break down the torque on the left with its two-dimensional definition. And I'll use 90 degrees as the angle between the force and the lever arm, since they're perpendicular to one another. The sine of 90 degrees reduces to 1, which allows us to chop that trig piece off and move forward using F times L. In the next step, both sides will be broken down even further, where we replace F with the weight of both objects, the lever arm with 3/4 times L sine theta, and the moment of inertia of both objects with the sum of their individual moments of inertia. And be aware that we're using the moment of inertia of a particle for the clay, because the problem description didn't tell us its size, so that's our only option. Since the rod and the clay have the same mass, then they will also have the same weight. So let's replace W both with 2mg. And I've also inserted the moment of inertia values over on the other side. Next is to simplify the expressions on both sides. And here we can cancel out a factor of m as well as a factor of L, which leads us to the following. The goal is to isolate alpha. So let's multiply both sides by 3 and divide both sides by 4. And then all that's left is to divide both sides by L. And there we go. There's our answer for the angular acceleration of part B. For part C, let's go back to our picture and flip the object around. We still have the weight, which acts from the center of mass, but this time it's closer to the point of rotation. And as a result, the lever arm becomes much shorter. Let's do the same trick of sliding the lever arm upwards, and we'll relabel it as 1/4 times L sine theta. To get the new angular acceleration, we go through the same steps involving the sum of torques equation that we did previously. There's still a single torque over on the left, which is about point Z, but since the clay is right on top of the point of rotation, it won't be included in the moment of inertia over on the right-hand side. Let's exchange the torque with F times L again, and I'll just skip the step that involves simplifying sine of 90 degrees, and then we'll insert our definitions here on both sides. We should simplify this as well as eliminate the factors of M and L like before. If we multiply both sides by 3 and then divide both sides by L, now we're all set. This is our answer for the angular acceleration of part C. Let's take a moment to compare our results before moving on to part D. Here's our two angular accelerations. If we switch out the fraction coefficients for numbers, well, then it's clear that the result from part C is slightly larger than the result from part B. At this point, we have all the information that we need to answer the question about balancing a pool cue. If we have the thin end on our finger, then the center of mass will be really far from the point of rotation, which means the moment of inertia and the torque are large, and the angular acceleration is small. If the angular acceleration is small, well, then it takes a longer amount of time for the pool cue to completely tip over. In other words, we have more time to react and stop that from happening. If we flip the pool cue the other way around, well, we get the opposite situation. The center of mass is now closer to the point of rotation, which results in a smaller moment of inertia and torque and a larger angular acceleration, which means we have less time to react if it starts to tip over. So that explains the difference between these two situations, and part D is now done. Here's the first part of our solution card, which contains the answers for parts A, B, and C. And I've also included a second part to the solution card, which has a condensed explanation for the answer to part D. That's everything for today, guys. Thanks for watching. I'll see you in the next one.